Ever find yourself, like, blown away by how much your computer can actually do at once?
It is pretty amazing.
Like right now, I bet you've got a bunch of programs running, probably streaming music, maybe even editing a video, and it's all, like, totally fine.
Mm-hmm.
And the crazy thing is, most of us don't even think about what's making that all happen behind the scenes.
Yeah, the unsung hero of our digital lives, the operating system.
The OS. And that's exactly what we're diving deep into today.
Buckle up.
So no better place to start than the beginning, Ray. What exactly are we talking about when we say operating system?
Well, our sources define an OS as the essential software layer. It's like the middleman between you, the user, and all that complicated hardware that makes up a computer.
So basically, without the OS, it'd be like trying to speak a completely different language to get your computer to do anything.
Exactly. Like imagine having to write lines of code just to save a file or open a web browser. Talk about a steep learning curve.
And that actually brings up a really interesting point, right? This whole idea of bridging the gap between humans and hardware, that's actually what led to the creation of operating systems in the first place.
Absolutely. Early computers, those were some seriously complex machines.
Oh, I bet. Like only a select few could even attempt to use them.
Exactly. And as programmers started to develop more and more complex software, they realized that they needed a better, more efficient way to interact with the hardware.
It's kind of like needing a translator, right? Someone, or in this case, something, to mediate between two parties who speak totally different languages.
That's a great way to put it. And that's essentially what an operating system does. And to solve this communication problem, OS developers came up with some seriously ingenious concepts.
Okay, like what?
Two of the most important being abstraction and virtualization.
Ooh, those sound kind of intimidating.
They sound a lot more complex than they actually are.
Okay, good. Break it down for us. What's abstraction all about?
Abstraction is all about hiding the really complex details of what's happening behind the scenes. It gives the user a simplified interface.
So instead of needing to know every single line of code, the OS is like, don't worry, I got this, and just shows us what we need to see.
Precisely.
So what's a real-world example of that? Because I feel like we see abstraction everywhere, but maybe just don't realize it.
Think about it like using a pre-made spice blend when you're cooking. Instead of having to measure out 20 different spices individually, you just use a spoonful of the blend.
Right. Like, I don't need to know the exact proportions of every single spice. I just want to sprinkle on some Italian seasoning and call it a day.
Exactly. The blend simplifies the process, and you don't need to know every single detail about what's in it.
Okay, so if abstraction is like the pre-made spice blend of the OS world, what about virtualization?
Virtualization takes that concept of abstraction a step further. It's like having multiple chefs who need to share a single kitchen, so you set up separate workstations for them.
Ah, so even though there's only one oven, each chef has their own designated space to work and prep, like they have their own little world within the kitchen.
You got it. And that's kind of what virtualization does. It creates this illusion of having multiple resources, even when you're working with a limited amount of hardware.
And that is why, my friend, we can listen to music, browse the web, and edit a document all at the same time.
Exactly. The OS is juggling all these tasks behind the scenes, making it look effortless to us.
And it's all thanks to those virtual environments the OS creates. I mean, it's pretty mind-blowing when you think about it, right?
It is pretty elegant how it all works. The OS can juggle all these different tasks and allocate resources effectively because it can create these separate spaces for everything.
Which actually brings us to another crucial role of the OS. The ultimate resource manager. It's like the OS is this master conductor making sure every instrument in the orchestra is in sync and no one's stealing the show for too long.
I like that analogy. It really captures the essence of what the OS is doing.
So let's break it down. We know computers have a limited amount of resources, right? Things like CPU power, memory, that kind of stuff.
Absolutely. And just like a conductor has to decide how much time each section of the orchestra gets, the OS has to figure out how to distribute those resources fairly. It's got to make sure that all the different programs and tasks you're throwing at it can run without, crashing the whole system.
Right. Because we've all been there when the computer just freezes up because we've asked it to do too much.
Exactly. And that's where multi-programming comes in. It's like the OS's secret weapon for multitasking.
Okay, so multi-programming is like the OS version of a multitasking superhero. I like it.
Basically, it allows the OS to keep multiple programs loaded in memory at the same time.
Hold on. At the same time. But how does it manage that?
It switches between them really rapidly, crazy fast. So fast that it creates this illusion that they're all running simultaneously.
Whoa.
So, let's say one program is waiting for data from the hard drive. While that's happening, the OS can quickly give another program a turn to use the CPU.
So it's never really letting anything sit idle. It's all about maximizing efficiency.
Exactly. And if we take multi-programming a step further, we get something called time sharing, which is also often referred to as multitasking. This is where the OS is switching between programs so quickly that it really does create the illusion of everything happening simultaneously.
It's like the OS is some master illusionist, making us think our computers are capable of way more than they actually are at any given moment. But it's this illusion that allows for such a smooth and productive computing experience, right?
Exactly. And speaking of smooth sailing, have you ever noticed how your computer slows down when you have, like, a zillion tabs open?
Oh, tell me about it.
That's a prime example of the OS's resource management skills being pushed to their absolute limit.
It's like trying to make a 5-course meal in a tiny kitchen with only one burner.
That's a great way to put it. Things are bound to get a little slow. The OS is doing its best to allocate resources fairly, but there's only so much it can do.
So we've got to cut our OS some slack sometimes?
Absolutely. It's working incredibly hard behind the scenes to keep our digital lives running smoothly.
It really makes you appreciate just how crucial these invisible forces called operating systems really are. I mean, they bridge the gap between us and this complex hardware, they manage resources like master conductors, and they even create the illusion of a seamless computing experience. It's pretty remarkable.
I agree. Operating systems are definitely the unsung heroes of our digital lives.
But now I'm curious, we've been focusing on like traditional computers this whole time. What about the future? Things are changing so quickly in the tech world.
You're right, things are evolving rapidly. And as we move into a world of even more powerful and complex technologies like quantum computing and advanced AI, the role of the operating system will undoubtedly need to evolve as well.
Quantum computing. Okay, now that sounds intense. What would an OS even need to do differently in that world? Like, how is that even possible?
Well, for starters, imagine the challenges of managing resources when you're not dealing with ones and zeros anymore, but with qubits.
Qubits.
Qubits are the building blocks of quantum computers. They can exist in multiple states at once. It completely changes the game.
Okay, so instead of juggling tasks like a chef, now the OS has to be like a quantum orchestra conductor or something, trying to harmonize the chaos of infinite possibilities.
That's a fantastic way to think about it. The complexity of these future systems would require operating systems to become even more sophisticated. Resource allocation, task scheduling, overall system management, all of that has to be taken to a whole new level.
It's pretty mind-blowing to think about how these basic principles we've been discussing, things like abstraction, virtualization, resource management, how will they be applied and adapted in these new computing paradigms?
It's going to be fascinating to see how it all unfolds. And it's not just about managing the hardware itself. As AI becomes more prevalent, operating systems might need to start mediating between human users and AI agents.
Whoa, so instead of just managing the technology, the OS might have to start navigating the complexities of human-machine interactions.
Exactly. It's about ensuring that AI algorithms are used ethically, transparently, and in a way that benefits humanity as a whole.
So we're talking about the OS evolving from this behind-the-scenes manager to like a digital diplomat, negotiating this complex relationship between humans and machines.
Precisely. The future of operating systems is full of incredible possibilities and challenges. And who knows what amazing innovations will emerge as we continue to push the boundaries of technology.
Yeah. It's incredible to think that something as fundamental as the operating system, something most people don't even realize is there, is going to play such a huge role in shaping the future of technology.
Absolutely. It's like the foundation upon which all of this amazing technology is built. And like any good foundation, it needs to be strong and adaptable to support whatever comes next.
So where do you think things are headed? I mean, what might operating systems look like in, say, 10, 20 years? What kind of challenges will they face?
Well, that's the million-dollar question, isn't it? It's tough to predict the future with any certainty, especially in a field as fast-paced as technology. But I think it's safe to say that OS developers are going to have their work cut out for them.
Okay, so no crystal ball, but what are some of the big questions that researchers are grappling with right now?
One of the biggest challenges is going to be figuring out how to design operating systems for these incredibly complex, powerful systems of the future, like quantum computers. We're talking about a whole new level of complexity compared to the computers we use today.
Right, because it's not just about making things faster or more efficient anymore. It's about figuring out how to manage and harness these entirely new types of computation. It's pretty mind-blowing stuff.
It really is. And then there's the whole issue of artificial intelligence and its increasing integration into our lives. Operating systems might need to evolve to manage these AI agents, ensuring they operate safely, ethically, and transparently.
Right, because we don't want our OS to accidentally unleash a robot uprising or anything like that.
Yeah. Exactly. It's about striking that balance between innovation and responsibility. We want to push the boundaries of what's possible, but we also need to make sure that these powerful technologies are used for good.
Absolutely. So it seems like the future of operating systems is going to be a wild ride, but hey, that's what makes this field so exciting, right?
Exactly. It's a constantly evolving landscape full of challenges and opportunities. And who knows, maybe one of our listeners will be the one to develop the next groundbreaking OS that changes the world.
Wouldn't that be something? Well, on that note of inspiration, I think we've given our listeners plenty to think about today.
I agree. It's been a fantastic deep dive into the world of operating systems, both present and future.
And I have to say, I have a newfound appreciation for the complexity and importance of the OS. It really is the unsung hero of our digital lives.
It truly is.
So to all our listeners out there, next time your computer is taking a minute to load or your phone is being a little glitchy, remember, there's a whole lot going on behind the scenes, and it's all thanks to the magic of the operating system. Until next time, keep exploring, stay curious, and as always, thanks for joining us on The Deep Dive.
Ever get the feeling that, like, with our computers, we're only seeing the tip of the iceberg?
Totally.
We click, we drag, we type, but, like, under the surface, there's this whole other world keeping everything humming along. And that, my friends, is the fascinating world of operating systems.
Or OS for short.
OS for short, exactly. And today we're diving deep, peeling back the layers of what's happening behind your screen. So think about it this way. You wouldn't, like, try to drive a car without knowing there's an engine under the hood, right?
Right.
The OS is that engine. It's managing your web browser, your files, how your software talks to the hardware, everything.
Yeah, and it's incredible how often we just take it for granted.
Mm-hmm.
I mean, most of us use computers every single day, and this system is working tirelessly behind the scenes to keep everything running smoothly.
That is so true. So in this deep dive, we're breaking down the structure of an OS, demystifying some of those terms you might have heard but maybe don't totally get.
Absolutely.
By the end, you'll see those everyday actions you take on your computer in a whole new light.
For sure.
Okay, so let's start with the part we interact with the most. The good old graphical user interface.
GUI.
Yeah, the GUI. It's all about being user-friendly. You've got your icons to click, windows to resize, that whole intuitive point-and-click world. But that's really just the tip of the iceberg, isn't it?
It is. It's designed for ease of use, absolutely. But underneath that, there's this much more powerful tool. You get way more control if you know how to use it.
You're talking about the shell, right?
Exactly.
Where you can type commands directly. I'll admit, that's always seemed a little intimidating, like something only hardcore coders really mess with.
Right, I get that.
Huh.
But here's the thing. Even if you're not a coder, even if you never write a single line of code, understanding how the shell works, the philosophy of it, can make you a power user.
Okay, I'm intrigued.
It's all about efficiency and automation. Like, imagine being able to rename hundreds of files at once or setting up these really complex file backups. But you could do it all with a single command.
Wow.
In the UI, you'd be stuck doing that manually one by one.
That's a really good point. Okay, so we've got the friendly GUI, we've got the efficient shell, but to really truly understand the OS, we got to go deeper, right into the heart of it all.
We have to.
And that, my friends, is the kernel.
Here's where things get really interesting. The kernel is the core of the OS. It manages everything from memory allocation to how your computer talks to its hardware. It's like the brain, the heart, and the immune system all rolled into one.
Oh, so it's making sure that all the other programs are, like, playing nice and sharing the computer's resources.
Precisely. It enforces the rules. It makes sure that no single program can just, like, hog all the resources, or worse, wreak havoc on your whole system.
Yeah.
And it does this through what are called privileged instructions.
Okay, privileged instructions. That sounds serious.
It is.
Break it down for me. What are we talking about here?
So think of it this way. These are special commands that only the kernel is authorized to execute. It's like a VIP pass to the computer's hardware.
Okay.
It prevents just any random program from messing with really critical functions.
Yeah. Ah, that makes sense.
This is actually a big part of why it's so difficult for viruses to really mess with your computer at a fundamental level. The kernel is like this powerful line of defense.
I never thought about it that way, but it makes perfect sense. So the OS is constantly running interference, keeping everything running smoothly, even when we have no idea it's even happening. That's kind of amazing.
It really is. And to fully understand how this whole symphony of software operates, we need to dive into how programs actually communicate their needs to the kernel.
Which brings us to
Just some calls.
system calls. Is that like some kind of techie hotline?
Not quite, but I like where your head's at. Imagine you're at a restaurant, you're ready to order, you don't like, barge into the kitchen and start cooking, do you?
And not unless I'm feeling particularly bold or hangry.
Right. Instead, you tell the waiter what you want, and they relay that to the kitchen.
Okay.
That's basically what a system call is. It's how applications, politely request services from the OS without crashing our metaphorical kitchen.
So the app tells the OS what it needs. The OS, with the kernel as head chef, obviously whips it up and everyone's happy.
Exactly. It's all about maintaining order and efficiency. But, just like in a real restaurant, sometimes things don't go exactly according to plan.
Oh, tell me about it.
You might spill your drink, the chef might burn the entree.
Okay, now you're just making me hungry. But I see where you're going with this. Our computers, they have those uh-oh moments too.
They do. And that is where interrupts come in.
Interrupts.
Yeah.
Like when you're telling a really good story and someone just cuts you off.
Well, the OS wouldn't be that rude. But, yeah, you've got the right idea. Interrupts are events that demand the OS's immediate attention.
Okay.
It could be anything. It could be a finished task, an error message.
Wait, hold on. So you're telling me even if I make like a simple math error, like the dreaded divide by 0, that triggers one of these interrupts?
You bet it does. In fact, that would cause a very specific type of interrupt. It's called a trap. Think of it as like the OS's way of saying, whoa there, buddy, you're about to break the laws of mathematics. Let's just pause and reassess.
And I thought my math mistakes were bad. Good thing the OS is there to prevent like a total system meltdown from every errant keystroke. So we've got these system calls, smoothly placing orders, keeping things running, and then we've got interrupts acting as kind of like the emergency alerts when something needs immediate attention.
Exactly. And what's really remarkable is just how often this is happening constantly. The OS is monitoring for these events all the time, ready to react in a fraction of a second to keep your digital world spinning.
It really is mind-blowing when you stop and think about it. The OS is like the silent guardian, right?
Totally.
Juggling requests, managing resources, putting out fires left and right, and it makes it look so easy.
It's a testament to how elegant computer science really is when you get down to it.
It is.
I mean, think about what we've just done. We started with clicking icons on our screen, and now we're talking about the GUI, the shell, the kernel, system calls, interrupts, this whole world that most people never even think about.
Right.
And yet it's powering our digital lives. It's pretty amazing.
It really is. We started with that car engine analogy, but now I'm picturing something even more intricate, like, I don't know, a massive air traffic control system.
Oh, yeah.
Carefully guiding each plane to its destination, making sure that nothing collides.
And just like air traffic controllers need to understand how each plane works, its capabilities, having even this basic understanding of how an OS manages resources, I think, can make all of us better computer users.
Yeah.
More informed computer users, for sure.
That's a really good point. Knowing that the OS is juggling all these processes in the background, it definitely makes me think twice about running like a million apps at once.
Right.
Or falling for those like speed up your computer gimmicks.
Exactly. You start to understand that your system resources are finite and something's got to give.
So true. So as we wrap up here, what would you say is like the most important takeaway for our listeners today?
I think the biggest thing is just to remember that there is so much more happening beneath the surface of your computer screen than meets the eye. And gaining even this basic understanding of how your OS works, it can give you a much deeper appreciation for how complex, how powerful the technology we use every day really is.
Absolutely. Next time I see that little spinning wheel, I'm not going to just sigh impatiently. I'm going to give a little nod to the OS, working tirelessly behind the scenes to keep my digital life running smoothly.
I love that.
Thanks for joining us for this deep dive into the amazing world of operating systems. Until next time. All right, let's jump right in. Today, we're tackling operating systems.
Ah, yes, the unsung heroes of the digital age, right?
Totally. They're like the stage crew of our computers, phones, everything.
Working tirelessly behind the scenes so we can, browse cat memes and stuff.
Exactly. But seriously, it's fascinating stuff, and this excerpt you've sent me, it's like a history book of operating systems.
It is. It talks about 5 distinct generations, from the first clunky computers to what we have today.
5! Okay, so back in the, like, dinosaur days of computing, what kind of OS were we rocking?
Well, picture this. It's the 1940s. Computers were these massive machines filled with vacuum tubes, took up entire rooms.
No kidding. I bet the electricity bill is scary back then.
Oh, you have no idea. Get this, those early computers, they didn't even have operating systems as we know them.
Wait, what? No OS? How did they even...
It was wild. Programmers had to interact directly with the hardware, using machine language. Super complicated.
Sounds like a nightmare. So basically, no Facebook for them, huh?
Pretty much. Imagine trying to program the EIATs, one of the first computers ever built. No operating system, just you and thousands of vacuum tubes.
Okay, yeah, no thanks. So how did we go from that to, well, what we have now?
That's where the second generation enters the scene. Transistors started replacing those bulky vacuum tubes. Smaller, faster, the drill.
Right, transistors, those tiny little, what do they do again?
They're like tiny electrical switches controlling the flow of information. More transistors, more processing power, faster speeds. It's a beautiful thing.
Okay, yeah, more power, faster speeds. This is starting to sound a little familiar.
It all builds on itself. And with these faster machines, we needed better ways to manage them. Cue the second generation of operating systems.
So what did they come up with? Was it like voice commands, touch screens?
Not quite. Think punch cards and batch processing. Sounds a bit archaic, right?
Programming by index card, basically.
Exactly. It wasn't pretty, but it was a step forward.
Baby steps, right? It's amazing how far we've come.
It really is. And it's all about making these complex machines easier to use for us humans. That leads us to the third generation. Things start looking a little more familiar here.
This is where we finally get keyboards and monitors, right?
Big O. Computers shrink even further. Keyboards become a thing. Monitors, too. We're talking interactive computing now.
So instead of feeding punch cards to a giant machine, you could actually, sit down and type?
You got it. And operating systems had to evolve too, right? They had to support these new ways of interacting.
Makes sense. So was this like the dawn of the personal computer?
Getting closer. It's like laying the groundwork. We're talking multi-user systems. Multiple people could use the computer slowly but surely.
Can you imagine sharing a computer with like a whole office?
Oh, the agony of waiting. But hey, it paved the way for what came next, the revolution of the personal computer.
And that, my friend, is where the GUI, the graphical user interface, makes its grand entrance.
Yes. The fourth generation. This is where we get the computers we know and love. Windows, icons, the mouse. It changed everything.
It's funny to think about how revolutionary that was back then. Clicking on icons instead of typing out code. Now we just take it for granted.
Totally. But that's the fourth generation in a nutshell. Bringing computers into our homes, our offices. Operating systems had to become user-friendly.
It's like they went from being tools for scientists to something anyone could use.
Exactly. But technology never sits still, does it?
Never a dull moment, right? And speaking of which, this excerpt keeps mentioning something called Moore's Law. How does that fit into all of this?
Moore's Law. It's like a prediction, a prophecy that has driven the evolution of computers and, by extension, operating systems for decades.
Okay, so break it down for me. What exactly is this Moore's Law?
In the simplest terms, it predicts that the number of transistors, remember those tiny switches, on a chip doubles roughly every 2 years.
So more transistors, more power, faster speeds. That's why our phones today are more powerful than those room-sized computers from before, right?
You got it. It's also the reason we're constantly bombarded with new phone models and upgrades. They keep pushing the limit, squeezing more transistors onto these tiny chips.
It's both impressive and a bit overwhelming at the same time.
Totally.
Yeah.
But it makes you wonder, can it go on forever?
That's what I was thinking. There's got to be a limit, right? We can't just keep making things smaller and faster forever.
You're hitting on a crucial point. Moore's Law has held true for an amazingly long time. But we're starting to bump up against the laws of physics. You can only make a transistor so small.
So what happens when Moore's Law hits a wall? What does that mean for operating systems?
That's the million-dollar question. It's something that keeps OS developers up at night. For one, it could mean the end of the constant upgrade cycle we're used to.
Wait, no more new phone every year? What will I spend all my money on?
Right. But on a serious note, it means we need a new approach. Instead of relying on hardware getting faster, we need to get smarter with software.
So OS developers need to become even more creative, more resourceful.
Exactly. Squeeze every ounce of performance out of what we have. It's a new era of innovation, and honestly, it's going to be fascinating to watch.
I bet. But it also sounds incredibly challenging. It's like they've been playing one game, and now the rules are changing.
That's a great way to put it. They need new strategies. But here's where things get even more interesting. We've been talking speed, processing power, but the world of operating systems is about more than just that.
Oh, what else is there?
Diversity. We focused on PCs, laptops, smartphones, but operating systems, they're everywhere.
Yeah.
And just like you wouldn't use a truck to deliver a pizza.
You need the right tool for the job. I get it.
Exactly. Different tasks, different OS designs.
Yeah.
It's all about finding the perfect match.
Okay, now you've got me curious. What kind of specialized operating systems are we talking about?
Well, let's start with the opposite of your smartphone,
Right.
the mainframe. These are the heavy lifters, the massive computers used by banks, governments, big corporations.
Handling tons of data, keeping everything running.
Exactly. Their operating systems are all about stability, security, handling massive amounts of information. They're like the foundation of the digital world.
Wow. So mainframes and their OEs, they're all business then.
Pretty much. Now, on the complete other side of the spectrum, you have real-time systems.
Real time. What are those used for?
Think your car, airplanes, even medical devices. Their job is to react instantly to what's happening.
Okay, so high stakes. How are their OCs different?
Speed and reliability are critical here. Even a tiny delay could be disastrous. These operating systems, they're designed for instant responses, no time for lag or errors.
It's like having a super responsive assistant, but for machines. Amazing. What other specialized OS are out there?
Let's talk about sensor networks.
Sensor networks, like those things that track your steps and stuff.
Kind of. Think environmental monitoring.
Right.
Each sensor might have its own little operating system, all working together. Air quality, temperature, you name it.
So it's like the Internet of Things, but powered by a hidden network of operating systems.
Bingo. Efficiency, low power, distributed processing. That's the name of the game for these specialized OS.
This is blowing my mind. I never realized how diverse the world of operating systems really is.
It's pretty remarkable. And we've only scratched the surface. There are operating systems for everything. Self-driving cars, robots on factory floors.
Yeah.
It's really a testament to how creative OS developers are, constantly pushing the boundary.
It's like a whole secret world right under our noses. We've got these big, powerful OS running the show, and then these tiny ones and sensors all working together. It's pretty amazing.
It is. It really highlights just how crucial operating systems are on every scale, whether it's global networks or your fitness tracker.
Exactly. The unsung heroes of our digital lives.
Couldn't have said it better myself.
Hmm.
We might not see them, but without them, well, our digital world would simply stop.
So after this deep dive, I'm looking at all my devices differently now. It's like knowing the secret code.
I love that. And it's true. Once you understand operating systems, you see their influence everywhere. But here's something to think about. As technology keeps evolving at this crazy pace, what will the operating systems of the future look like?
Okay, now you're really making me think. What's next for this hidden world of OS? Any predictions?
Well, one thing is for sure, things are only getting more intertwined. We're heading toward a world of ubiquitous computing devices, constantly talking to each other, working together.
So what does that mean for operating systems?
They need to be ready for anything. Adaptable, flexible, intelligent.
So less like a conductor, more like a jazz musician, just going with the flow.
Exactly. Imagine operating systems that learn your habits, anticipate your needs, maybe even fix themselves when something goes wrong.
Okay, now that's both super cool and a little creepy.
Right. But it's incredibly exciting. We're on the verge of a whole new era where the possibilities are practically limitless. And who knows, maybe you will be the one designing those future operating systems.
Huh. I think I'll leave that to the experts, but this deep dive has definitely sparked my curiosity. I might even have to do some more exploring on my own.
That's the spirit. Curiosity is what drives discovery. Who knows what hidden wonders you might uncover in the world of technology?
Well said. For me, it's definitely a newfound appreciation for those operating systems that make everything possible. It's like they've always been there, but now I understand the language.
And that's the power of a good deep dive.
Couldn't agree more. So, to our listener, the next time your phone acts up or your computer crashes, take a breath and remember. There's a whole lot more going on beneath the surface than you might realize. And hey, maybe it'll spark a little curiosity in you too.
Until next time, happy exploring.
It's true, we do take it for granted. But back then, it was a huge G deal.
Absolutely. The fourth generation was all about making computers mainstream. And operating systems, they had to keep up.
No more punch cards, thank goodness.
Thankfully not. But speaking of how things have changed, this excerpt keeps mentioning Moore's Law. Ever heard of it?
Yeah, it rings a bell. It's about, like, how technology keeps getting faster.
Exactly.
Right.
It's kind of wild, actually. Moore's Law basically predicts that the number of transistors, remember, those tiny switches that we can fit on a chip, doubles every 2 years or so.
So more transistors, more processing power, things get faster. And cheaper, too, right?
Precisely. It's why today's smartphones are more powerful than those room-filling computers from back in the day.
It's kind of mind-blowing when you think about it, but this Moore's Law thing, it can't go on forever, can it?
You're asking the right questions. It's been shockingly accurate for decades, this prediction,
Sure.
but there are limits, right? Physical limits.
Right, like how small can those transistors actually get?
Exactly. We're talking atoms here. At some point, you hit a wall.
Okay, so let's say, hypothetically, Moore's Law, it fizzles out. What happens then? What about operating systems?
Well, for starters, it could mean the end of those constant upgrades. No more needing the latest and greatest every year.
Whoa, hold on. Are you saying no more new phone every year? What am I going to spend all my money on?
Right. But seriously, it's a huge GE shift. It means operating systems. They need to change too.
How so?
Instead of relying on faster hardware, we need to design smarter software. Squeeze every drop of performance out of what we have.
So a whole new set of challenges for OS developers.
You could say that. It's a whole new ball game. But here's the thing. We've been so focused on processing power, on speed, but operating systems, it's not just about that. It's also about diversity.
Diversity? Wait, what do you mean?
We've been talking PCs, laptops, smartphones. But operating systems, they're everywhere. Just like you wouldn't use a wrench to hammer in a nail.
You need the right tool for the job.
Exactly. Different tasks, different OS designs.
Okay, so like what kind of specialized operating systems are we talking about?
Well, let's jump to the opposite end of the spectrum from your smartphone, the mainframe.
The mainframe.
These are the workhorses of the digital age. Big, powerful computers used by banks, governments, any organization that needs to process massive amounts of data.
So not your average laptop then. What about their OS?
Their operating systems are all about stability, security. They're the backbone of the digital world, really.
Wow, so mainframes and their operating systems.
Yeah.
All business, no play.
Pretty much. Now, on the flip side, you have real-time systems. These are the OS working behind the scenes in your car, airplane, even medical devices.
Wait, really? My car has an operating system.
It does, and it's critical that it works flawlessly. In these real-time systems, speed and reliability are everything.
Because even a tiny glitch could be disastrous.
Exactly. These operating systems, they have to react instantly, no room for error.
That's intense. Okay, so we've got mainframes for crunching huge amounts of data, real-time systems for keeping things running smoothly. What else is out there?
Ever heard of sensor networks?
Sensor networks.
Sync environmental monitoring. Each individual sensor, whether it's measuring air quality or temperature, could have its own tiny operating system, all working together.
So it's like the Internet of Things, but powered by a network of like mini operating systems.
Exactly. These networks need specialized operating systems that are super efficient, use very little power, and can process information from tons of different sources.
It's amazing, right? From these giant mainframes to tiny sensors, who knew operating systems were everywhere?
They really are. It just goes to show you operating systems are kind of running the show no matter what kind of device we're talking about.
Totally. They're like the unsung heroes of our digital lives, quietly making sure everything works as it should.
Couldn't put better myself. It's easy to forget about them, buried deep inside our devices, but without them, well, our digital world would fall apart pretty quickly.
No doubt about it. So, after all this, I'm looking at my phone, my laptop, everything differently. It's like I've unlocked a secret level of understanding.
Huh. I like that.
Yeah.
And it's true. Once you get into the world of operating systems, you start to see them everywhere working their magic. But here's something to think about. As technology keeps changing, what's next for operating systems?
Okay, yeah, good question. What does the future hold for OS? Got any predictions?
Well, one thing's for sure. The line between hardware and software, it's getting blurry. We're moving toward a future of, total connectivity. Ubiquitous computing, they call it.
Ubiquitous computing. That sounds intense.
It is. Devices constantly talking to each other, working together. And for operating systems, that's a whole new challenge.
So, what, they need to be even more adaptable, even more flexible?
Tenfold. They need to be smart, able to learn, maybe even predict what we need before we know it ourselves.
Okay, that's getting a little sci-fi now.
Right. But it's also exciting. Think about operating systems that can anticipate your needs, learn your habits, maybe even repair themselves when something goes wrong. The possibilities are huge.
That's wild. So we've gone from punch cards to potentially self-aware operating systems. What a journey.
It's pretty incredible when you think about it. And the best part is, we're just getting started. Who knows what amazing innovations are right around the corner?
That's the truth. Well, for me, it's definitely a newfound appreciation for the complexity and the importance of operating systems.
And that's what we like to hear. It's about peeling back the layers, understanding the systems that make our digital lives possible.
Absolutely. So, to everyone listening, next time your phone's acting up or your computer crashes, take a breath. Remember, there's a whole lot more going on under the hood than you might realize. It's a hidden world, but it's fascinating stuff once you start to dig a little deeper.
Couldn't agree more. And who knows, maybe this deep dive will inspire someone out there to become the next great OS innovator. Until next time, keep exploring.
Ever look at your computer and wonder what's really going on in that sleek little box?
Yeah.
Well, today we're diving deep into the world of computer architecture.
Nice.
Going beyond just clicking and scrolling, you've sent in some really fascinating technical documents, and we're here to decode all the jargon and uncover those aha moments hidden within.
Yeah, it's like, it really is like this intricate puzzle, isn't it?
It is.
Each component is, perfectly designed to work in sync with the others.
Right.
And understanding these pieces and how they interact can make you, I think, a much more informed user. And you really start to appreciate the brilliance behind the technology we use every day, I think.
Absolutely. So no more treating our computers like magical black boxes.
Right.
Let's start by understanding the core players.
Okay.
Imagine a bustling city, right?
Well.
Okay. We've got the CPU, the central processing unit. This is acting as the mayor's office.
Okay.
Making decisions, directing traffic.
Okay, I like it.
Then we have memory. So that's our library.
Okay.
Storing information the CPU needs quickly.
Right.
And finally, storage devices. These are like the city's warehouses,
Right.
storing things long term.
Yeah, makes sense. It's a good analogy.
Yeah.
But what's really fascinating is how these components communicate, right?
Yeah.
And how they coordinate their actions. They don't just sit around waiting for instructions.
Right.
They operate in like a really dynamic environment.
Right.
Where unexpected events can occur at any time.
Yeah.
And so that's where this concept of interrupts comes into play.
Interrupts. Sounds a bit disruptor, doesn't it?
Well, yeah. I mean, in a way they're designed to be.
Okay.
Think of it this way. Imagine the CPU as a chef juggling multiple dishes on a stove.
Yeah.
Right?
Okay.
Suddenly the oven timer beeps,
Uh-oh.
the phone rings, and at the same time, someone's at the door.
Oh my goodness.
These are all interrupts demanding immediate attention.
Wow. Okay, I'm starting to see the parallel here. So how does the CPU handle these interruptions without, well, completely burning dinner?
Right. Well, that's where the interrupt vector comes in.
Okay.
It's like a well-organized switchboard.
Okay.
So each type of interrupt has a unique number, right?
Right.
And this vector, which you sent us a figure of, figure 1.4.2,
Right.
this directs the CPU to the right handler for that specific interrupt. So it makes sure that the CPU doesn't waste precious time figuring out what to do. It knows right away, oh, this is this kind of interrupt. I need to go over here.
So it's like having a dedicated receptionist who immediately knows who to call based on the situation.
Exactly. But it gets even more interesting. Not all interruptions are created equal, are they?
Right.
I mean, just like a chef prioritizes a burning pot over, someone ringing the doorbell.
Right.
The computer has a system for interrupt priority levels.
So how does it decide which interrupt gets handled first?
Right, so that's determined by a combination of hardware and software.
Okay.
So some devices, like those that manage critical functions, these are designed to trigger higher priority interrupts.
Okay.
Others might be assigned priorities based on the software running at the time.
It's all like meticulously designed to ensure the system runs smoothly, even when it's being bombarded with all these demands.
Wow.
Yeah.
It's amazing. You know how the computer has this system for prioritizing, like it's an emergency, just like we do, right?
Yeah, absolutely.
But all this talk about the CPU juggling tasks and everything makes me wonder, where does it actually store all this, like, data and instructions that it needs to operate.
Right.
That's where memory comes in, right?
Exactly. Yeah. If the CPU is like, imagine it as a chef, right?
Sure.
Memory is like a combination of the counter space they're working with and their refrigerator.
Okay.
It holds all those ingredients and recipes that the CPU needs to use right now in the moment.
So that's our RAM, random access memory.
Exactly, yeah. RAM is that counter space, that handy countertop.
Right.
Easy to access, but it's also temporary.
So once the power goes out, everything on that countertop is gone.
Oh,
Oof.
okay.
Which is why we need more permanent storage, and that's where our hard drives and SSDs come in.
Right.
They're like the pantry and the freezer, storing things long term.
Okay, so we've got our temporary workspace, our RAM, and then we've got the long-term storage of the hard drives and the SSDs.
Right.
But I've also heard about this thing called the memory hierarchy.
Yeah.
What is that all about?
That's a great question. So the memory hierarchy is really all about how we balance speed, the cost of the memory, and the capacity.
Okay.
So imagine kind of like a pyramid, right?
Okay.
Like in that figure you sent, 1.4.3.
Uh-huh.
At the very top, closest to the CPU, we have the smallest, fastest, and most expensive memory.
Okay.
That's called cache, and that's reserved for the most frequently accessed data and instructions.
So it's like having your spices that you use all the time within arm's reach when you're at the counter.
Exactly. Yeah, got it. And then as we move down our pyramid, we have main memory, which is our RAM.
Okay.
And that's larger and slower than cache.
Yep.
But it's still much faster than secondary storage, your hard drives and SSDs, which are down at the bottom.
Okay, so the further down the pyramid we go, it's kind of like we get more storage space, but it costs us speed.
Exactly. That's
Yeah.
exactly right. And the computer's really smart about this. It actually moves data between these levels to try to make sure that the CPU always has really quick access to what it needs.
Wow.
It's like this constant dance of optimization happening behind the scenes.
That's wild. And it makes me realize that, all these components need to be talking to each other really well for this whole system to function. So we've talked about the CPU and memory, but what about everything else? Like, how does the computer handle input-output from devices?
Right.
Keyboards, monitors, even external storage. How to do it?
Yeah, so that's where the I/O structure comes in, right?
Yeah.
Often called input-output. It's essentially how the computer interacts with the outside world.
Right.
Taking in information, sending information back out. Think about it like the transportation system of our city.
Okay.
With roads, bridges, delivery routes, all making sure things are running smoothly.
And just like with the city, we don't want traffic jams slowing down the performance of our computer, right?
Exactly, yeah. Efficiency is key. And that's actually where something called direct memory access, or DMA, comes in.
Okay.
It's like a game changer when it comes to moving large amounts of data.
Okay, I'm intrigued.
Yeah.
How does DMA work? What makes it so special?
Okay, so imagine this. Instead of each data package, right, being individually inspected and processed by the CPU,
Okay.
like going through customs,
Right.
DMA is like having a dedicated express lane that allows those packages to completely bypass the CPU and just travel directly between the memory and the storage.
So it's kind of like a high-speed rail line for data.
Exactly. Yes, exactly. This frees up the CPU to go and focus on other tasks, which significantly speeds up the data transfer. And this innovation was huge back when CPUs were much slower. But today, even though CPUs are much faster, DMA is still super crucial for freeing up those CPU cycles to go tackle those, more complex computations.
Yeah, that's really cool. That's fascinating. It's like DMA created this shortcut, bypassing the usual bottleneck we always hear about.
Yeah, exactly. And it's like this kind of innovation is a really good example of how computer architecture has actually evolved to solve all these performance challenges that we have.
Right.
And speaking of evolution, DMA gets even more interesting when you pair it with modern switch architectures.
Okay, I'm all ears. What's so special about switch architectures?
Well, remember how we were talking about the bus being like the transportation system of our city?
Right.
Okay, so think of a traditional bus like a single highway
Okay.
with multiple exits, right? As more and more devices want to connect, that highway can get really congested.
That makes sense. Everyone's trying to use the same road.
Exactly. So now imagine that we could replace that single highway with this whole network of interconnected high-speed rails, right?
Oh.
That's essentially what a switch architecture is doing.
Wow.
It allows for much faster, much more direct communication between all those different components, especially when we're transferring these large amounts of data with DMA.
So instead of everybody trying to merge onto the same crowded highway, they've got their own dedicated route they can take.
Exactly. You got it. And that significantly improves the efficiency, the bandwidth, and allows these modern computers to just handle all these crazy data-intensive tasks that we throw at them.
It's amazing.
From, streaming 4K videos to running complex simulations, it's incredible.
From cityscapes to chefs to high-speed rails, I have to say, these analogies have really helped.
Good.
They painted a really vivid picture of how computers work. I feel like I'm starting to understand, the elegance behind the complexity of it all.
Yeah, and that's the beauty of it all, right?
Yeah.
Understanding computer architecture. It's like taking something that seems like this magical black box, and you open it up and it's like, wow, there's this whole intricate system of interconnected parts in here.
Right.
Each one playing such a crucial role.
This deep dive has been, it's really opened my eyes to that. We've gone from the CPU managing, all these interrupts, like a multitasking chef,
Yeah.
to the memory hierarchy, like this intricate dance,
Right.
to high-speed data transfers, DMA, switch architectures.
Right.
Wow.
Yeah, absolutely. And you know what? What we've explored today, it's really just the tip of the iceberg.
Really?
There's so much more out there to uncover. I mean, from different CPU architectures like RISC and CISC to the finer points of memory management, caching strategies, it goes deep.
That's both really exciting and a little daunting to realize how much more there is to learn.
Yeah,
But I don't know, that's the beauty of technology, right? There's always something new to discover.
absolutely.
Hmm.
And as technology is advancing at this incredible pace, who knows what crazy innovations await us?
Right.
Perhaps, quantum computing will completely revolutionize computer architecture as we know it.
Yeah.
It's a very fascinating time to be, involved in following all this.
It certainly is. So to all of our listeners out there, we really encourage you, keep that spirit of curiosity alive. Don't just use your computers. Explore them,
Absolutely.
Delve a little deeper into these topics that pique your interest.
Yeah, you might be surprised what you find.
You might be amazed by what you find.
Yeah.
Well said. And on that note, I think it's time for us to sign off.
Okay.
Until next time, keep exploring this amazing world of technology.
Absolutely. See you next time. All right, everyone, welcome. Ready to dive deep into the world of tech. Today, we're going to unpack something that sounds kind of, complicated, but it's actually all around us. Computing environments.
And it's funny, most of us don't think twice about them until something goes wrong, right?
Exactly. It's like we just want our phones and laptops to work. No one's really thinking about all this stuff happening behind the scenes. But you know what? The story of how we got here, how we went from those clunky old computers to what we have today, it's actually pretty wild.
Yeah.
Our source material dives right into this, talking about it. The typical office, the workplace has totally transformed. Like, remember when work meant you were chained to a desk, stuck with this giant PC in a cubicle?
Oh, yeah. And forget about working from home. Our source actually talks about this back in the day. Remote access was so limited. If you needed something from the office network, you were basically out of luck.
I can't even imagine. Today, so many of us can work from anywhere. And it's not just that our home setups, they're often more powerful than what entire businesses had just a few years ago. We've got super fast internet, home servers, multiple devices. I mean, it's crazy how much has changed, even in the last decade.
And it's not just about the technology itself, right? This whole shift to, what do they call it, ubiquitous computing, it's completely changed how we work, how we connect with colleagues, even just how we think about information. We're constantly connected, which has its pros and cons, for sure.
For sure. And with that constant connection comes a whole new set of challenges like cybersecurity. Which, speaking of, our source mentions firewalls. Can you break down for us what exactly is a firewall and why do we even need them?
Sure, think of a firewall like a security guard for your network, your own personal internet traffic controller. It's basically a barrier that controls what goes in and out of your network, making sure that only the good guys, the legitimate requests can get through.
So it's like a filter, keeping the bad stuff out. That actually makes cybersecurity a bit easier to understand, especially with how our homes are becoming more and more connected. Smart refrigerators, security cameras, you name it.
Exactly. As the line between our work life and home life gets blurrier, understanding all these underlying systems like firewalls becomes so important for everyone, really.
Definitely. And speaking of blurring lines, let's talk about those computers we carry around every day, our smartphones and tablets. I mean, it blows my mind to think that these little things have more power than entire rooms full of equipment did just a few decades ago.
It's true. Our source even talks about this. We can do almost anything on these devices now, right? We stream movies, video chat, you can even experience augmented reality. It's incredible.
It's easy to get caught up in how cool it all is, though, and forget that even these pocket powerhouses have their limits.
Oh, for sure. As advanced as mobile operating systems like iOS and Android have become, they still can't quite match up to traditional PCs when it comes to pure processing power and how much they can actually store.
Right. Like if I try to download a massive game or edit a really big video on my phone, I hit those limitations pretty quickly.
Exactly. I think our source mentioned this. You might have, 256 gigabytes of storage on a high-end phone these days, which seems like a lot, but compare that to a desktop computer that could have 8 terabytes of storage. That's a massive difference.
Wow, that puts it into perspective. So that's got to be why cloud storage is becoming so essential, right? It's like our phones are pushing us toward the cloud just because they can't handle everything on their own. But how does all of that work on the back end?
Well, a lot of it comes down to this fundamental concept called the client-server model.
Okay, yeah, I've definitely heard that term thrown around, but to be honest, I've never fully grasped it.
I think it's one of those things that sounds way more complicated than it actually is. Think about checking your email, right? So your email app, whether it's on your phone or your computer, that's the client. It's basically making a request saying, hey, I want to see my messages. And where are those messages actually stored? They're on a really powerful computer, or more likely a network of computers, and we call that the server. That server is the one that actually fulfills your request to see your emails.
So it's like I'm asking a librarian, the server, to find a specific book for me, my email.
That's a great way to put it. And the thing is, this client-server model, it's not just for email. It's actually how we interact with websites, online services. Pretty much everything online relies on this model.
Wow, I never realized how fundamental it really is. Which makes me think of something else we hear a lot about the cloud. Is that connected to the client-server model?
Absolutely. The cloud is basically taking the client-server model and, putting it on steroids. Imagine a network of servers, but we're talking massive, mind-blowingly big, all working together to store and process data. That's the cloud.
So we're talking like a mega server.
Kind of, yeah. It's more like a team effort, a whole bunch of servers all working together instead of just one, which makes it incredibly powerful. Think about when you're using Spotify or Netflix, you're not downloading their entire libraries onto your phone, right?
No way, my phone would be totally full.
Right. That's the cloud in action. You're streaming all that content from this massive network of servers, just accessing what you want when you want it. And the source actually gives a crazy example. Amazon has this cloud platform, EC2, and they have thousands of servers storing data in the petabytes.
Okay, I get that a gigabyte is a lot and a terabyte is even more, but petabytes, that's a whole other level. What can we even compare that to?
It's honestly hard to even wrap your head around. Imagine the Library of Congress, millions of books, photos, recordings, all that stuff. Now imagine hundreds of thousands of libraries of Congress all connected together. That's the scale of data we're talking about with cloud computing.
Wow. Okay, that's just mind-blowing. Makes our phones and laptops seem so tiny in comparison.
In a way, they are. But this interconnectedness, it's what makes them so powerful, right? But we've talked about the computers in our homes, the ones we carry around. What about the ones that we don't even really see? Like the ones embedded in, everything.
You mean like the computer that's in my refrigerator? Or my car? Yeah, I'll admit, those aren't usually on my mind.
Right. Those are called real-time embedded systems. They're everywhere, working behind the scenes constantly. Think about your car engine, for example.
It's kind of wild to think there's a whole computer in there, controlling my car while I'm driving. What makes them real-time, though?
Well, it all comes down to speed, how quickly they have to react. In a normal computing environment, if there's a little delay, it's probably just annoying. But with these real-time systems, a delayed reaction, that could be really bad.
Yeah, that makes sense. I definitely don't want my brakes to be slow because my car's computer is taking a break.
Exactly. Real-time embedded systems are designed to react instantly, based on data from sensors, so things like your brakes, airbags, even your windshield wipers, they work exactly when they're supposed to.
That's a whole side of computing I never really thought about. But it's so important for our safety and, let's face it, for just making our lives easier.
Absolutely. And these systems, they're everywhere. Medical devices, airplanes, traffic lights, you name it. They might be hidden, but they're a crucial part of how everything works.
This is really making me appreciate just how many different kinds of computing environments there are out there. I mean, we've gone from those giant computers that took up entire rooms to ones we can fit in our pockets, and now these invisible systems embedded in everything around us. It's crazy.
It really shows how far we've come. And the pace of innovation, it's not slowing down anytime soon.
It really makes you wonder, what's next? I mean, we've already gone from computers that took up entire rooms to ones we wear on our wrists. Where do we even go from here?
That is the million-dollar question, isn't it? The source actually touches on this a bit, especially as our homes and cities get, well, smarter, more interconnected.
Yeah, it's exciting, but also a little bit, I don't know, unnerving. Like, we've talked about all the good stuff, the convenience, the progress, but what about the other side of that? With all this data flying around, what about privacy?
Oh, absolutely. That's a huge concern. As we rely more and more on cloud computing, on all these systems being connected, data privacy becomes, well, it becomes essential. The source even mentions this. We need strong security measures. And more than that, we need to think ethically about how all this data is collected, stored, used. It's not just about the technology itself, it's about how we use it.
Yeah, it feels like we're in uncharted territory in a lot of ways. Creating these amazing things, but also having to figure out, I don't know, the rules of the road as we go.
Exactly. And it's on all of us, really. The people creating these systems, they have a responsibility to build them ethically. And us, the users, well, we have to be aware of what data we're sharing, how it could be used.
It's like this deep dive has given me more things to think about than, actual answers.
Yeah.
But that's a good thing.
I think so too. Sometimes it's not about finding all the answers, right? Sometimes it's about sparking that curiosity, getting people to look at the world around them and really think about how these systems work, how they impact our lives.
Well said. A huge thanks to you for taking us on this deep dive into computing environments. It's been amazing.
My pleasure. I always enjoy getting to talk about this stuff.
And to everyone listening, thanks for coming along on this journey, exploring the world of computing, from those clunky PCs to the cloud and beyond. Until next time, stay curious. Ever wonder what makes the digital world tick?
Well, we're about to find out.
We're about to embark on a deep dive into the fascinating world of open source operating systems.
Yeah, it's more than just, free software.
We'll uncover not just what they are, but why they matter, and how their story is really the story of computing itself.
It's like peeking behind the curtain of the software that we all use every single day.
And I have to admit, I always thought open source and free software were basically the same thing.
Yeah, that's a really common misunderstanding.
Is it?
Yeah, all free software is open source, but not all open source is free software.
Right.
The key difference lies in the licensing and the freedoms that they grant.
Licensing. That's where things always get a little murky.
Think of it this way. Imagine a cookbook. Free software, as championed by Richard Stallman,
Okay.
emphasizes the 4 freedoms: using, sharing, modifying, and sharing those modifications.
Okay.
It's like saying, here's the recipe, go wild, make it your own, and share it with the world.
Right.
Open source might give you the recipe, but there might be rules. Like, you can make it for yourself, but you're not allowed to sell it, for example.
Okay, so Stallman is like this revolutionary chef advocating for culinary freedom.
Exactly.
But why is this so important?
That's a good question.
Why should anyone care about these freedoms?
Because software's power. It shapes how we communicate, how we learn, even how we think.
That's true.
And Stallman recognized that restricting access to the building blocks of software is like restricting access to knowledge itself. The 4 freedoms help ensure that software can be a tool for everyone, not just a select few.
It makes you appreciate that early era of computing in a new light.
Yeah.
It sounds like it was a much more open and collaborative environment, almost like a digital potluck.
Exactly. Sharing code and building upon each other's work was the norm.
Huh.
But then, as the software industry grew, the profit motive kicked in, and companies became more protective of their code, treating it like a secret sauce rather than a shared recipe.
Yes, like the Wild West of software development suddenly got fenced off.
Right.
But then, just as the landscape seemed destined for domination by these software giants,
Yeah.
a new player emerges, Linus Torvalds, in this little thing called Linux.
And what's remarkable is how Linux embodies this David versus Goliath narrative.
It really does.
This wasn't some well-funded corporation. Right. It started as a student project, a single person challenging the status quo of software development.
Yeah.
And it resonated with people.
It's like the digital equivalent of a band starting in a garage and becoming a global sensation.
Exactly.
And a big part of that success was the internet, right?
Absolutely. Imagine if that garage band could instantly share their music with the world and have millions collaborate on writing new songs.
Right.
All for free.
Wow.
That's essentially what happened with Linux. The internet became this breeding ground for collaboration with developers all over, contributing to the kernel, the heart of the operating system.
And that kernel is now running everything from servers to smartphones. It's mind-boggling.
It's everywhere.
Speaking of unexpected places, this next bit really threw me for a loop. Did you know that Mac OS, Apple's operating system, known for its sleek design and, let's face it, closed ecosystem, actually has roots in the open source world?
It's true. And it's a surprisingly tangled history.
Really?
That goes back to BSD Unix, a system that actually predates Linux.
So BSD Unix is like the lesser-known ancestor of Mac OS?
You could say that, yeah. What's the story there? Well, BSD Unix emerged from the University of California, Berkeley. Think of it as a branch of the original Unix family tree.
Okay.
But unlike its commercial cousins, BSD Unix was open for anyone to use, modify, and distribute.
Huh.
This openness sparked a wave of innovation.
Yeah.
But it also led to legal battles over who owned what.
Sounds messy.
Yeah.
So how did this lead to Mac O, which is about as far from a free-for-all as you can get?
Well, the legal wrangling around BSD Unix ultimately led to the creation of Darwin, a streamlined and robust operating system based on the BSD codebase. Apple saw its potential and adopted it as the core of macOS.
Wow.
So every time you use a Mac, you're interacting with a descendant of this open source pioneer.
It's amazing to think about this lineage.
Right.
How ideas from those early days of open collaboration are still shaping the technology we use today. But it's not just about these big names, right? There's a whole ecosystem of open source operating systems out there.
Absolutely. Think of it as a buffet of operating systems.
Okay.
Need rock solid security.
Yeah.
There's an open source operating system for that.
Okay.
Want to revive an old computer? There's one for that too.
Why?
And because you have access to the source code, the possibilities for customization and learning are pretty much endless.
It's like the difference between just driving a car and being able to take it apart, see how it works.
Yeah.
And even modify it to your liking.
Exactly. With open source operating systems, you're not just a user.
Right.
You're potentially a contributor, a learner, even an innovator.
Yeah.
I've seen countless examples of students who dove into open source projects just to learn.
Yeah.
And they ended up making significant contributions and even launching their careers that way.
That's incredible. It speaks to the empowering nature of open source. It's not just about the technology, right?
Right.
It's about democratizing knowledge and giving people the tools to shape the digital world around them. And this ethos seems to be spreading beyond just operating systems, wouldn't you say?
Absolutely. We're seeing open source principles popping up everywhere. From the scientific community, sharing research data and collaborating on algorithms, to artists and designers using open source tools to create, stunning visuals and music.
It's like this ripple effect, breaking down traditional barriers and fostering a more collaborative and interconnected approach to knowledge creation.
It is.
But like any powerful tool, open source must come with its own set of challenges.
Of course, yeah. Sustainability is a big one.
Yeah.
Open source projects often rely on volunteer contributions,
Right.
which can be difficult to sustain long term.
Right.
There are also concerns about security,
Yeah.
particularly with open source software being used in, critical infrastructure. And then there's the question of inclusivity.
Right.
How do we ensure that everyone benefits from this open ecosystem and that it doesn't inadvertently exacerbate existing digital divides?
That's a crucial point. Openness for openness' sake isn't enough.
Right.
We need to be mindful of the potential downsides and work towards creating a more equitable and accessible open source landscape.
For sure.
It makes you think about the future of technology and how these choices we make today about openness and collaboration will shape the digital world for generations to come.
Absolutely. And it's not just about technology. It's about how we as a society choose to approach knowledge, innovation, and our shared digital future.
It's a lot to ponder. We've journeyed from the early days of shared code to the rise and rebellion against proprietary software. We've explored the impact of Linux and the surprising lineage of macOS. And we've even peeked into the diverse world of open source operating systems beyond the big names. So much to think about.
And we've only scratched the surface.
I know.
The open source movement is constantly evolving,
It really is.
with new projects, challenges, and possibilities emerging all the time.
Which brings us to something we want you to think about.
Okay.
As you go about your day interacting with technology, consider this. How else is open source shaping your digital experience? From the apps on your phone to the websites you visit, chances are open source is playing a role.
So the next time you encounter something powered by software, take a moment to consider its origins.
Yeah.
Was it built on open source principles?
Okay.
What are the implications of that, both positive and potentially negative?
Food for thought. This has been our deep dive into the fascinating world of open source operating systems. Keep exploring, keep questioning, and keep diving deep into the technologies that shape our world. Welcome in, everyone, ready to dive deep. Today, we're tackling virtualization. Not just the buzzword, but what it really means. We're using operating system concepts, that tech Bible, to guide us.
Oh, great choice. Classic. It lays the groundwork and hints at how virtualization touches everything, even how the internet's evolving. It's wild.
Right. So reading through it, what's the core thing someone should know about virtualization? Like the essence of it?
You know, it might sound basic, but it's the decoupling, that separation between your computer's hardware and the software running on it. That's what makes the really cool stuff possible.
Decoupling, like giving them breathing room.
Yeah. Instead of one operating system tied to the hardware, you can run multiple at the same time. Each one tucked away in its own little virtual machine, like having several computers in one.
Okay, now I'm picturing it better. But why should someone care? What's the real-world impact of all this virtual juggling?
That's where it gets exciting. Think. Better security, using your resources way more efficiently, and even making software development faster.
Let's break those down, starting with security. The excerpts really highlighted that. What makes virtualization a game changer there?
Isolation, plain and simple. Think of virtual machines as, say, apartments in a building. If one has a plumbing problem, it shouldn't affect the others, right?
So a virus stuck in one virtual machine won't spread to others or even crash the whole system.
Exactly, a built-in wall against malware. And if something does happen, it's way easier to contain within that virtual space.
Makes sense. Now, the text mentioned virtual networks too. Those are key for letting these virtual machines talk to each other.
Definitely. Isolation is great for security, but they gotta communicate sometimes. Virtual networks let them do that safely and in a controlled way.
Like the hallways and intercoms of that apartment building.
Yeah.
Keeps things organized.
Perfect analogy. You need that balance.
Yeah.
Separate for safety, but connected enough to function.
Speaking of, let's talk resources. I was struck by how virtualization makes the most of your hardware. It's almost like squeezing more juice out of the orange, you know?
Totally. The old way, you had tons of computers barely being used. Virtualization lets you combine them, fewer machines, but each one running multiple virtual ones. More bang for your buck.
And that means saving money, I bet.
Oh yeah. Less hardware, less electricity, even maintenance is simpler. Businesses, data centers, they love that kind of efficiency.
And it's not just doing more with less, but doing it smarter. The book talked about live migration. What's that all about?
Now you're talking about flexibility. Imagine moving a virtual machine from one server to another while it's still running. No interruption, nothing. Like transferring an app from your phone to your computer mid-use.
Wow, that's impressive. A lifesaver if a server is overloaded or needs fixing.
Exactly. Everything keeps running smoothly, even when things are unpredictable. That's huge for businesses that can't afford downtime.
Yeah, like virtual machines are these old workhorses you can move around wherever you need them.
Exactly. And it's not just about managing servers better. Think software development, even how we install apps. It's changing everything.
Right. The excerpts talked about that digital sandbox idea. Developers can test stuff without fear of blowing up the whole system.
Exactly. Imagine testing new software or updates in their own little world. If it goes haywire, you just rewind the virtual machine back to how it was.
No more system crashes. That's got to be music to their ears.
Speeds everything up. New features, bug fixes, they all happen faster. And that means better software for everyone in the end.
Who doesn't love that? Now, the book also mentioned how apps are installed, even hinting at a future where it's as easy as plugging in a USB drive.
Oh, there's huge potential there. Imagine getting a virtual machine, everything already set up, no compatibility issues, no headaches trying to install things. It just works.
That would be amazing.
Yeah.
Software support would be a breeze. Though, wouldn't we need all virtual machines to be on the same page for that to work smoothly? Like some kind of standard?
You hit the nail on the head. The book actually mentioned this open virtual machine format. The idea is to make a universal standard, so any virtual machine runs on any platform.
Like having one adapter for all your gadgets, no matter the brand. Just plug and play. That would be revolutionary.
Right. It would be huge for innovation, more competition, which is good for everyone using this technology.
So we've got security efficiency, faster development, easier installation. What can't virtualization do?
Well, it's not magic.
Yeah.
But it's the foundation for something huge that's becoming a part of our lives. Cloud computing.
The cloud, where we keep all our pictures, stream our shows, even how businesses operate now. The book touched on this. How does virtualization make the cloud work?
Imagine a huge network of servers, all linked together, each one running tons of virtual machines. Those machines, they provide the resources for all the cloud services we use. Streaming, storage, it's all happening on virtual machines.
So my movie marathon is basically running on a virtual machine somewhere out there. That's wild. You don't even realize it's happening.
That's the beauty of it. It quietly scales up or down depending on what people need. Music streaming or a business app, it all runs smoothly.
It's like this invisible workforce, always adapting. We take it for granted, but it's incredibly complex stuff.
Absolutely. And it's not just those big services either. Think remote desktop access that uses virtualization too.
Oh yeah, they talked about that. Instead of having everything on your own computer, you access it remotely from a virtual machine somewhere else.
Yep. You're basically using a virtual desktop that lives on a server in a data center. Way more secure since none of your important stuff is actually on your own device.
That's a relief with all the hacking going around.
Yeah.
And it's perfect for working remotely, I'd imagine.
For sure. Work from anywhere, securely, and without any lag. That's the power of virtualization.
We've gone from virtual machines as these self-contained things to, like, the backbone of the internet. It's changing how we use tech completely.
It really is a huge shift. And as it keeps evolving, who knows what's next? It's exciting to think about.
It's mind-blowing, right? From those early ideas of virtual machines being like their own little worlds to this whole interconnected virtual world we're headed towards.
It shows you how powerful those basic tech ideas can be. Once you separate the hardware and software, the possibilities are endless. It can change everything.
And it's not just the tech itself. It's how we think about computing power, right? It's all more flexible, more accessible.
For sure. It's like instead of owning a car, you use a ride-sharing app. You're not limited anymore. You just tap into whatever you need when you need it.
Perfect analogy. Makes you wonder, as this gets even more advanced, what'll it change next in our digital lives?
That's the big question, isn't it? The part that got me thinking was the book mentioned virtualization could even change how we see reality itself. As these virtual worlds become more real, it makes you wonder how we'll work, learn, even just hang out with friends. It's a whole other level.
It does sound like sci-fi, but it's getting closer all the time. What seemed impossible before, suddenly is right around the corner.
Exactly. That's what's so cool about this field. It's not just the tech changing, it's how we think about things, what it means for society, even philosophy.
We've covered so much ground, from those security advantages of virtual machines to, wow, maybe even redefining reality. It feels like we're just scratching the surface, though.
That's what deep dives are for. There's always more to learn. That's how it should be.
For those who want to go even deeper, operating system concepts, our source today, that's the place to start. Really lays the foundation of how this all works.
Absolutely. And don't be scared of those technical terms like suspend, snapshot, all those. They sound jargony, but they're the building blocks of this whole future of computing.
Your keys to unlocking even more knowledge. Well, on that note, we'll wrap up our virtualization deep dive. Hope you enjoyed exploring it with us.
Until next time, keep that curiosity going and dive deep into the world of tech. Who knows what you'll find?
Okay, so picture this for a second. You've got the New York Stock Exchange, right? Buzzing with activity. And then in your hand, you've got a cutting-edge Android phone. And to top it all off, we're going to throw in the Large Hadron Collider, a machine basically built to uncover like the deepest mysteries of the universe. What could these possibly all have in common?
Well, it's definitely not some secret society of tech wizards, though that would be pretty cool, wouldn't it? The answer is actually a lot more common, and I'd argue even cooler. It's an operating system called Linux. You've probably heard of it. It's everywhere, quietly powering so much of our digital world. But most people don't really, understand what it is or how it got here.
Which is the perfect launching point for this deep dive. We're going deep into the world of Linux, all the way back to its origins. And our trusty guide for this journey is none other than Pasted Text, a treasure trove of insights on all things Linux.
We're talking about going back to the very beginning, back when a Finnish student named Linus Torvalds basically kickstarted a tech revolution. And get this, he did it all from his dorm room.
Okay, before we fire up the time machine and journey back to the early days of Linux, let's make sure everyone's got a solid handle on the basics. We hear this term tossed around all the time, but what exactly does an operating system actually do?
It's a great question, and it's actually simpler than it sounds. Think of it this way. Your computer is like a car, right? Well, the operating system is everything that makes that car go. It's the engine, the transmission, the electronics, all working together. It's the bridge between you, the driver, and all the complex machinery under the hood. Without it, you've basically just got a very expensive and very heavy paperweight.
Okay, that's a fantastic analogy. I'm never going to look at my computer the same way again. So we've got Linus, our dorm room revolutionary, building this engine for the digital world. But here's where things get really interesting. Instead of keeping his creation under lock and key, treating it like, a precious trade secret, he does something completely radical for the time.
Yeah, this was the early 90s, keep in mind. Back then, software companies were fiercely protective of their code. It was like their crown jewels. But Linus, he went in a completely different direction.
He flipped the script.
Exactly. He basically said, here, world, take this, it's yours. And I don't just mean the finished product. We're talking the complete blueprints, the source code, the whole shebang, all available for anyone to use, modify, and even distribute. He called it open source, and let me tell you, it sent shockwaves through the software world.
That is wild, especially for that era. Today, we're a bit more used to the concept of open source, but back then, it must have seemed like technological heresy.
It was a bold move, a real act of, I'd say, digital idealism. Linus truly believed that software development should be a collaborative effort, that by sharing knowledge, working together openly, we could create better, more innovative technology faster. And he wanted to make sure that this technology was accessible to everyone.
A noble goal, for sure. But idealism only gets you so far, right? Did this radical experiment actually work?
Oh, it worked. And then some.
Tell me more.
It's almost like a fairy tale, really. Word got out about this free and open operating system, and programmers from all over the world, they flocked to it.
Drawn in by the allure of the open source?
Precisely. People were finding and fixing bugs, adding features, porting it to new hardware, all at this incredible pace.
A global community of digital pioneers.
I love that digital pioneers. You're right. That's exactly what they were. And the speed at which they could move, the innovation they unleashed, it simply wouldn't have been possible with the traditional closed-door approach that most companies were using back then.
So we've got this global team of brilliant minds all working together on this open source operating system. But let's talk about the early versions of Linux itself. What was it actually like to use? Was it love at first boot?
Well, love might be a strong word. Remember, this is 1991. We're talking about version 0.01, the very first public release. And compared to the sleek, user-friendly operating systems we're used to today, version 0.01 was, shall we say, a bit rough around the edges.
Paint us a picture.
Imagine a world without a graphical user interface, without a web browser, without even the ability to easily connect to a network. That was Linux 0.01. It was like the Model T of operating systems, functional, sure, but a far cry from the Tesla Model S of today.
No internet access. Oof, that's a deal breaker for me, even back then.
It was a different time, but even in those early days, you could see the potential.
So what changed? When did Linux start to become more than just a geeky side project?
The turning point was version 1.0, released in 1994. This was a major milestone. It introduced a lot of fundamental features, most importantly, basic networking capabilities.
So now you can finally connect to the internet.
Exactly. And it wasn't just about browsing cat memes, though I'm sure those were popular even back then. This was a crucial step in allowing Linux to become a serious player in the internet revolution that was just starting to unfold.
Speaking of unfolding, wasn't version 1 also when they introduced that quirky odd-even numbering system that Linux still uses today?
You're right, they did. And it might seem a little strange at first, but there's actually a good reason behind it.
Enlighten us.
It's all about signaling the stability of a release. Odd-numbered versions like 0.01, 1.1, those were considered development releases. Open to change, experimentation, things could break. Even numbered versions, on the other hand, like 1.0, 2.0, those were the stable releases, ready for prime time.
A simple system, but effective. Kind of like a warning sign for users. Proceed with caution, you're entering experimental territory.
Exactly.
But let's be real, Linux was more than just a cool experiment, right? When did it really start to turn heads, to challenge the big dogs of the operating system world?
That's where Linux 2.0 comes in. Released in 1996, this wasn't just an upgrade, it was a statement. This was Linux putting the world on notice.
Okay, I'm intrigued. What made version 2.0 so special?
2 words. Multi-architecture.
Multi-architecture?
Yeah, it's a mouthful, I know. But it was revolutionary.
I'm guessing it means something more than just running on different types of computers.
You're catching on. You see, before version 2.0, Linux was basically confined to running on PCs with Intel-compatible processors. But version 2.0 changed all that.
So it was breaking free from the Intel cage.
Exactly. It was now capable of running on a much wider range of hardware, including, and this is a big one, systems using alpha processors, which were the darlings of the high-performance computing world at the time.
So instead of being limited to just one type of engine, Linux could now power a whole fleet of different vehicles.
A perfect analogy. And that wasn't the only trick up version 2.0's sleeve.
Oh, there's more.
Oh yeah, they were just getting started. Version 2.0 also introduced something called symmetric multiprocessing, or SMP for short.
SMP. Okay, you've got to break this one down for us.
Basically, SMP meant that Linux could now effectively use the power of multiple processors at the same time.
Okay, and why is that a big deal?
Think of it this way. Imagine you're working on a complex project, but instead of doing it all by yourself, you've got a whole team of people who can help you. That's what SMP allows Linux to do with processors.
So it's like dividing and conquering a task to get things done faster.
You got it. And as computers started to get more and more powerful, with multiple processors becoming more common, SMP was essential for unlocking that potential performance.
Okay, so we've gone from this bare bones system to this multi-platform, multi-processor powerhouse in just a few short years. The pace of innovation must have been incredible. Linux was really hitting its stride back then.
It was like a whirlwind of development. You had all these brilliant minds coming together, bouncing ideas off each other, pushing the boundaries of what was possible.
A global brain trust.
Yeah.
All fueled by open source.
Exactly.
So where did they go from there? What came next after that major leap with version 2.0?
Well, they didn't rest on their laurels, that's for sure. Versions 2.2, 2.4, 2.6, these were all about refinement, taking this already powerful foundation and making it even more robust, even more capable.
So less about flashy new features and more about the nitty-gritty details.
You could say that, but these details, they made a huge difference for users.
Give us some examples.
Sure, take SMP, for example, that symmetric multiprocessing we talked about earlier. They made significant improvements to SMP support in these later versions, which meant that Linux could really squeeze every last drop of performance out of those multiprocessor systems.
Because everyone loves a faster computer.
Right, exactly. But it wasn't just about speed. They also introduced something called journaling file systems around this time.
Okay, that sounds kind of technical.
It is, but it's actually a really elegant solution to a common problem.
Which is?
Data loss. Imagine this. You're working on an important document you haven't saved in a while, and suddenly, bam, your computer crashes.
Been there, done that. It's the worst.
The worst, right. Well, journaling file systems were designed to prevent that kind of heartbreak.
Okay, how so?
Think of it like a sophisticated journaling system, but for your computer's hard drive. It keeps a record of all the changes being made to your files. So if the system crashes or there's a power outage, you don't lose all your unsaved work.
That's incredibly clever. So it's like having a safety net for your data.
Exactly. It was a huge step forward in terms of data integrity and reliability. And of course, they also made significant improvements to memory management.
Memory management, that's how Linux uses your computer's RAM, right?
You got it. The more efficient the memory management, the faster and smoother everything runs. Your computer can juggle more tasks without slowing to a crawl.
So we've got less crashing, better performance, more efficient use of resources. It sounds like the Linux developers were really firing on all cylinders.
They were on a roll, that's for sure.
But I do have to ask about version 3.0. It just sounds so monumental. Did they do anything special to celebrate that milestone?
Oh, they did. Version 3.0, which was released in 2011, was a big deal in the Linux world.
As it should be. 2 decades of innovation, that's impressive.
It really is. And to mark the occasion, they introduced some pretty significant advancements, particularly in the realm of virtualization.
Virtualization. Okay, I've heard that term thrown around, but I'm not entirely sure I understand what it means.
It's actually a pretty simple concept once you wrap your head around it.
Hit me with it.
Imagine being able to run Windows on your Linux computer.
Hold on, are you saying I can have my Linux cake and eat Windows too?
Precisely. That's the beauty of virtualization.
Okay, my mind is officially blown.
Virtualization allows you to run one operating system, like Windows, inside another operating system, like Linux, as if it were just another program.
So it's like creating a virtual computer within your computer.
Exactly. It's like a digital nesting doll.
I'm never going to run out of computer metaphors at this rate.
And the best part is it opens up a world of possibilities.
Like what?
For developers, it's huge. They can test their software in different environments without needing to have multiple physical computers. And for everyday users, it means you can access software that might not be available for your main operating system.
So virtualization basically broke down the walls between these different operating system worlds.
It was a game changer, no doubt about it.
Okay, so version 3.0 was a pretty big deal, but what about version 4? Did they keep up that pace of innovation?
They did, though. By that point, the version numbers had become more about marking time, celebrating the ongoing evolution of Linux rather than signifying these massive overhauls.
So they'd reached a point where Linux was already incredibly stable, powerful, and versatile.
Exactly. They had laid the groundwork, and now it was all about continuous improvement.
But we've been talking a lot about the Linux kernel, and I think it's important to clarify something for our listeners.
Absolutely. What's on your mind?
Well, we've been so focused on this idea of the kernel as the engine of the operating system. But what about the rest of the car? What else is there?
That's a great point. The Linux kernel, as essential as it is just one piece of the puzzle.
Okay, so walk us through it.
The kernel, as we've established, is the heart of the system, right? It interacts directly with your computer's hardware, managing the CPU, the memory, all that low-level stuff.
The nuts and bolts.
Exactly. But to have a fully functional operating system, something you can actually use to get things done, you need more than just a kernel.
Like what?
You need other software. Things like a graphical user interface, so you're not stuck staring at a blinking cursor all day.
That does sound a bit tedious.
You need web browsers, text editors, music players, all the applications that they rely on.
So it's like the kernel provides the foundation, and then all these other pieces of software are built on top of it to create the user experience.
You got it. It's like building a house. The kernel is the foundation, and then you add the walls, the roof, the plumbing, the electricity, all the things that make it livable.
And this is where the collaborative spirit of open source really shines, wouldn't you say?
Absolutely. Remember the GNU project we talked about earlier?
The one that contributed so much to the free software movement.
The very same. Well, they played a crucial role in providing a lot of the software that, when combined with the Linux kernel, formed the complete Linux system.
So Linux wasn't built in a vacuum.
Not at all. It was a true community effort, with people from all over the world contributing their time, their skills, and their code.
It's amazing to think about all these different pieces, all these different contributions coming together to create something so powerful and influential.
It's a testament to what can be achieved when people collaborate openly and share their knowledge freely.
But let's be honest, building an operating system from scratch, even with all these open source tools available, it sounds a bit intimidating.
It can be, especially in the early days. You had to be pretty tech savvy to get a Linux system up and running.
So how did Linux go from this niche, hobbyist operating system to something that powers a significant chunk of the internet, our smartphones, and countless other devices?
That, my friend, is the million-dollar question. And it all comes down to the concept of Linux distributions. Distributions. Think of them like prepackaged Linux systems. Instead of having to build everything from scratch, you get a nice, neat package that includes the kernel, a user interface, and a curated selection of software, all designed to work together seamlessly.
So it's like choosing from a menu of options instead of having to order a la carte.
Exactly. You've got distributions like Debian, known for its stability and its focus on free software. You've got Red Hat, a popular choice for businesses and servers, known for its reliability and its enterprise-grade support. And then you've got Slackware, which is a bit more minimalist, more customizable. It appeals to users who really like to get their hands dirty and tweak every last setting.
So something for everyone.
Exactly. And these distributions, they were a game changer for the adoption of Linux.
How so?
Well, for starters, they made Linux a lot more accessible to regular users. You didn't need to be a command line wizard to install and use it anymore.
You could just pop in a CD or download an image and be up and running in no time.
Precisely. And they came with this other amazing thing, package management systems.
Package management, what is that? Some kind of delivery service for software?
Kind of. Think of it like an app store for your Linux distribution.
Okay, I'm listening.
So in the old days, if you wanted to install a new program on Linux, it could be a real hassle.
You'd have to search for it online, download it, make sure you had all the right libraries and dependencies, and then hope and pray that it didn't conflict with anything else on your system.
It was a recipe for disaster.
I can imagine.
But package management systems changed all that.
How so?
They basically took all the pain out of installing and managing software.
Okay, I'm intrigued. Give me the details.
So with a package management system, you can just open up a program, search for the software you want, click install, and boom, you're done.
No more hunting down dependencies or worrying about compatibility issues.
The package manager takes care of all of that behind the scenes and makes sure that you have all the right components, that everything is installed in the right place, and that everything works together seamlessly.
That's incredibly convenient.
It was a game changer for usability, and it's one of the main reasons why Linux became so popular.
So we've got this incredibly powerful, incredibly flexible, and now incredibly user-friendly operating system.
Don't forget about reliable.
Right, of course, reliable too. But there's one more piece of the puzzle we need to address.
And what's that?
The elephant in the room. The thing that makes Linux so unique. This whole idea of free software. We've danced around it a bit, but we need to dive deeper.
I'm with you. It's a fascinating and often misunderstood aspect of Linux.
So let's clear the air. When we say free software, what do we really mean? Is it like free beer, or is there a catch? And we're back. Diving right back into the fascinating world of Linux.
We've journeyed from those early experimental versions to a global tech phenomenon.
We've seen how Linux went from a dorm room project to a force to be reckoned with in the tech world.
All thanks to the power of open source and a whole lot of ingenuity.
But now it's time to bring it home. Where does Linux fit in our world today?
Well, it's not just about programmers and tech enthusiasts anymore, though they still play a huge role.
Because I don't see a whole lot of Linux laptops at my local coffee shop.
True, you're not as likely to see Linux running your average person's desktop. But behind the scenes, that's a different story.
Oh, tell me more.
Linux has quietly become the backbone of the internet as we know it.
Okay, now that's a bold claim. What makes you say that?
Think about the websites you visit, the apps you use, the online services you rely on every single day. Chances are a good chunk of them are running on Linux servers.
Really? I had no idea.
It's everywhere. It's incredibly stable, it's reliable, and it's incredibly efficient, which makes it perfect for large-scale web infrastructure.
So the next time I'm checking my bank account online or ordering takeout or binge-watching my favorite show, there's a good chance it's all running on Linux behind the scenes.
Very likely, yes. And it's not just servers. Remember how we talked about Android phones earlier?
I sure do. What about them?
Well, those also rely on Linux.
Wait, really? I always thought Android was its own separate thing.
It is, in a way, but Android actually uses a modified version of the Linux kernel as its foundation.
So under the hood, it's still Linux.
In essence, yes. Google takes that core Linux kernel and adds its own layers of software on top to create the user interface and all the apps and services we associate with Android.
Mind blown. I'm never going to look at my phone the same way again.
And it doesn't stop there. We're talking embedded systems in everything, from cars to smart refrigerators to those internet-connected light bulbs that you can control with your phone.
You're saying Linux is even in my fridge?
It's possible. It's become the go-to operating system for a huge range of devices.
It's like it's infiltrated every aspect of our digital lives.
In a good way, of course. It's a testament to its versatility and its adaptability.
So it's not just about servers and smartphones. It's also about scientific supercomputers.
Right.
Crunching massive data sets, modeling complex systems, all that good stuff.
Exactly. Linux has become essential for scientific research and development. It even powers the International Space Station.
Okay, now that's just impressive. So what's the takeaway here? What does the story of Linux tell us about innovation, about collaboration, about the future of technology?
I think it shows us that the old way of doing things, the closed-door approach where companies hoard their knowledge and their code, it's not the only way, and it might not even be the best way.
You're saying open source, this radical idea of transparency and collaboration, it's a viable alternative.
More than viable. I think Linux proves that it can be incredibly powerful when you bring people together, when you encourage them to share their ideas freely, when you work towards a common goal, you can achieve amazing things.
And Linux is a shining example of that. It's a testament to what's possible when we embrace the spirit of open source.
Exactly. It's about breaking down barriers, sharing knowledge, and working together to build a better future, one line of code at a time.
I love that. It's inspiring to think about the impact this one operating system, this open source project, has had on the world. And it all started with a student in his dorm room, tinkering away on his computer.
It's a good reminder that innovation can come from anywhere, and that even the smallest spark can ignite a revolution.
Well said. That's all the time we have for today, but what a journey it's been. From humble beginnings to a global phenomenon, Linux has truly left its mark on the world.
And its story is far from over, which is an exciting thought.
It is. So until next time, keep exploring, keep learning, and most importantly, keep that open source spirit alive.